In this video, we're going to learn how to use cylindrical shells to calculate the volume of a solid of revolution. And the plan is to examine a solid of revolution for which the washer method is impractical. So that'll motivate a new method. And this new method of using cylindrical shells, we'll figure out how to use that to find the volume. We're going to contrast this new method to the washer method and develop a heuristic technique for sort of setting up a shell integral. And we're going to look at examples. So here's a nice cubic. We could just we're going to create an example here of a solid of revolution. So we could write down a cubic that intersects the x-axis at 1, 2, and 4, and we could scale it by a factor of 2 to make it slightly larger. We could multiply out the terms, get this nice cubic, and now let's take the region that's trapped right here above the x-axis between x equals 1 and 2. We're going to take that region and we're going to rotate it around the y-axis to obtain a shape that sort of resembles a bundt cake. And our goal is to find the volume of this cake. If you're familiar with the method of washers, you could think, well, we could slice this along sort of parallel to the tabletop and get a bunch of washers and build up the cake that way. And so we could use this washer method to find the volume. So we could thicken these washers up, and we'll notice that the skewering axis, these shapes all stack up along the perpendicular to the y-axis, and indeed a thickness we could think of the thickness as being delta y. And so what's going on here is we're going to wind up integrating with respect to y to execute the washer method. Everything we do needs to be done in terms of y then. So what are our limits of integration? Well, we're going to start at y equals 0, and then we're going to have to go up to here. Well, what do we need here? That's a local max, and we're going to need to actually find a local max. So we could set dy dx equal to 0, find the value of x, which we would then plug into the function value, and there's our upper limit of integration. And it's a little concerning that this expression is more complicated than we might hope, but nevertheless it wasn't that hard. So we've got an upper limit of integration. So we're going to continue on with our method of washers and see where we go. So we could think of an outer face, because when you put in a washer, you can see that that sort of outer face represents the outer radius. And there's going to similarly be an inner face, for which we find an inner radius. So there are these two radii that we need to use the washer method. And we need to find these radii functions in terms of y. We need to solve for x in terms of y. So for points on the curve, we need to be able to solve for x in terms of y to plug this into the washer method. So let's think about that for a second. It's a cubic polynomial. For a given y, there could be as many as 3 different values of x. So you know this has to be somewhat complicated. And in fact, there is a formula called Cardano's formula that helps you solve cubics. So here's our bundt cake. And let's say we were interested in finding the outer radius. How could we solve this cubic for x in terms of y? We could apply this Cardano's formula, and unbelievably you get something. If I didn't make a mistake in copying it down, there it is. And you'll notice that it's remarkable that there are non-real numbers in this expression, and yet the value of that function is real. This is just an amazingly complicated formula to give us the outer radius function as a function of y. So what does our washer method do for us? We're going to integrate from 0 to 4/27 7 root 7 minus 10. The outer radius squared. We have to square this mess. And then on top of that, there's still a similar mess for the inner radius squared. So this is just a calamity. There's no way we're going to use the washer method. In theory it works, but this cannot be the way we're going to find this area practically. So we're going to come up with a different method. And the method's based on a shape that we might call a shell. So if we take a rectangle and spin it around the y-axis, you're going to get something that we're going to call a cylindrical shell. Now, if you think about this, you realize there's qualitatively nothing different. A cylindrical shell and a washer are qualitatively the same, but you might say that a shell is a tall, thin washer, if you like. Really what's going to make the difference is the way we put these shells together to fill out a solid of revolution. So let's find the volume of a shell. So what we could do is we could move in and chop the shell and unroll it, and we would get a box. And a box is easy to find the volume for. You can just multiply the 3 dimensions. And 2 of these dimensions already exist in the rectangle we use to spin around the axis. The only question is, what's this last dimension? So we could call it the height and the thickness. Let's call it delta x for reasons which will become apparent later. So those dimensions we'll call h and delta x, and the real question is, what's this last dimension? Well, it's pretty clear in the picture that that dimension comes from the circumference over here of this shell. So if we give the radius a name, r, then the circumference is 2 pi r, and there's our missing dimension. So the volume of a shell should be 2 pi r times the height times the thickness, and there's our formula. But there's really a couple issues here. We didn't really define r that well. I just, are we talking about the inner radius, the outer radius? Where exactly does r, are we measuring r? And then the whole act of unrolling isn't really well defined because the shape changes. The inside of the shell is going to stretch, the outside of the shell is going to compress, so we were really sort of playing fast and loose. We expect if delta x is small, this should be a good approximation, so perhaps we should be willing at the moment just to say that this is approximately equal, but we should be more careful about this. So let's look at a shell again. We'll just go through this very carefully. Here's the height and the thickness. We won't need the height for what we do next, so we're going to sort of put it in the background. Let's define the outer radius and the inner radius, and then define a third radius, which would be the average of these two. And you can express the outer and inner radii in terms of delta x this way. So what would be the volume of the whole cylinder if you were to look at the whole profile on the outside? Well, it would just be pi times the outer radius squared times the height h, which you could expand, and you'd get this expression. We could play the same game with the inner cylinder. So we could find the inner volume. These are just, we're just finding volumes of cylinders. And now the observation is the shell is obtained by letting the inner cylinder drop out of the outer cylinder. That's what you have left is the volume of the shell. Now when you subtract these two quantities, there's some cancellation, and you're just going to get 2 pi r h delta x. What is r? R is this middle radius, the average of the inner and the outer. So there you have an exact formula for the volume of a shell in terms of the sort of inner or the middle radius, the average of the inner and the outer radii. So there you go, and to be more conceptual about it, perhaps we should label it this way so that you sort of have a coordinate-free, variable-free formula. The volume of a shell is 2 pi times the middle radius times the height times the thickness. We're going to need this several times in the rest of the video. So back to our bundt cake. Now we can imagine how to build up the bundt cake out of shells. And you'll notice these are stacking from the inside out concentrically. Let's build a Riemann sum approximation using shells. So the first thing we're going to have to imagine is how to thicken these shells up. So we're going to add up the volumes of all these shells, and that'll hopefully give us an approximation of the volume of the bundt cake. What's the volume of just one of these shells? So let's concentrate on one of the shells we're using here. So remember our function, let's call it f, and we've got one particular argument that'll show up in the Riemann sum. So let's say it's the midpoint of that subsegment, and we know that the volume of a shell is 2 pi times the middle radius times the height times the thickness. Well, what's the middle radius? In our picture, it's pretty clear that the middle radius is simply xk. So there's our middle radius. What's the height? The height is simply the value of the function at xk. So let's put that in. What's our thickness? Our thickness is actually just the width of our subinterval. So if we call that delta x, we would have this as our expression for the volume of one of the shells that shows up. Now, what do we do with this? We can imagine what the Riemann sum is going to look like. So we've got a common thickness of delta x. We pick the midpoint of each of our subintervals, and now we're simply going to apply the formula we just achieved for each of the pieces. So we've got 5 shells that we're going to add up, and we're going to apply the previous slide to each of those. Now what's going on here, we could use sigma notation to collect this together, and you'll notice this is a Riemann sum. There's our Riemann sum approximation for the volume of the bundt cake. Now you could have any number of divisions, so let's say that top number is n, and now the question is, what happens as you take the limiting value as n goes to infinity? Well, we get an integral. You should be able to recognize how the parts of the Riemann sum turn into an integral. And we're integrating from a to b. Remember where that Riemann sum occurred. It occurred on the interval from a to b. So there's our integral, which is going to give us the volume of the bundt cake. Now in our example, f of x had a formula. It was a cubic. So we can actually substitute that in. And so now we're just going to simplify that a little bit. And we're going to leave the details for a little exercise, but that's just a polynomial, and it might be a little tedious, but it's certainly not as catastrophic as the washer method was, and so you're going to get a number relatively easily. And that's about 7.749. So let's look at another example of how to use shells. Let's suppose we have the curve y equals x squared, and sine of pi over 2x, let's see, pi over 2 in there as a coefficient, which means the period of this sinusoidal function is going to be 4. So here's a quick sketch of this graph. Now it's pretty obvious these two graphs intersect at the point 0, 0 and 1, 1. And what we're going to do is we're going to take this region between those 2 points, so to speak. We're going to take this green region and we're going to rotate it around the vertical line x equals 2. So what we get is another sort of bundt cake shape. So it's going to look something like this. And we want to figure out how to use shells to find the volume. So how do shells fit? They're going to fit like this. They're going to fit together like this to sort of approximate the volume. Let's calculate the relevant quantities for one particular shell. So remember, the volume of a shell is 2 pi times the radius times the height times the thickness. Let's imagine, given an x, what a typical shell looks like. It's important to be able to sort of visualize these shells. All right, what's the thickness? Well, the thickness is just going to be delta x. We're just going along that direction. It's how much x changes, so that's going to be our thickness. Our radius, 2 minus x. What's our height? It's a little more subtle in this problem. There's a top and a bottom. To find the height, we'll just take the top minus the bottom. But that's going to be sine of pi over 2x minus x squared. So there's our formula for height. Now we can just put this all in. There's our radius, there's our height, there's our thickness. So there is our volume for a shell. A Riemann sum, a typical Riemann sum might look something like this. It's not so important to be able to write out the Riemann sum as it is to imagine how that turns into an integral. Now the only trick here, really the only slippery part of this, is the limits of integration. On what interval are we integrating? And you'll notice that our Riemann sum was based on x sub k's that fell between 0 and 1. In other words, that interval takes care of all of our shells, and so this integration should take place from 0 to 1. So there's our integral. And we're going to leave it as an exercise to evaluate this. Warning, there's going to be integration by parts involved. But that's your volume integral for this shape. So here's a warning. Shells are not cross-sections. Now, washers and discs are cross-sections, so let's return to this method of washers and discs to see what we're talking about here. So these cross-sections here all line up, and if you imagine skewering them, so to speak, then you can see that the skewering axis is sort of the u-axis here. So that's what we mean by skewering. And the volume then would be cross-sectional area, which, for what it's worth in this case, is going to be pi outer radius squared minus inner radius squared as a function of u. And then you're going to integrate through the extent from one end of the shape to the other, so from the smallest value of u to the largest value of u. So Washers are cross-sections, and when you do cross-sectional area, you integrate from one end to the other. Shells are not cross-sections, however. So let's call these axes U and V. Why? We're going to be abstract about this because you should really get away from the notion that there's something inherently valuable about the name of a variable. So we're going to use U and V for our variable names here on the axes. And we're going to take this shape and we're going to spin it around the horizontal line V equals C. And we're going to get something that looks like this. And what we want to do is we want to set up shells. So how do shells work? We're going to go back to the cross-section. You can see that you can build shells up this way to get your figure. And the question is, what's the skewering axis in this case? What do we mean by skewering axis? So imagine that you have all your shells are sort of sitting there loose and you want to put them on the grill. So what you're going to need to do is figure out how to sort of skewer them so that they're held together. And that's what we mean by the skewering axis. And you know, a legitimate question is, wait a minute, there are a lot of different ways to skewer this to hold it in place, and that's true. However, if you go back to the original two-dimensional set of options, of all those, you really only have two options there. You've got the vertical or horizontal lines that you could use to skewer, and of those, it's the vertical line that you want. So the skewering axis is the V-axis in this case. So we're going to integrate with respect to V. But here's the warning. Shells are not cross-sections, so we're not going to integrate from one end to the other. Shells are not stacked from one end to the other. They're generated concentrically, either inside out or outside in. And this is important when you set up your limits of integration. So how do we set up a shell integral, and how do we recognize the limits of integration? So let's look at a typical term in the Riemann sum. So there's our skewering axis. That means our integration is going to be with respect to V. And for a particular value of V, you get a shell. Now remember, the volume of a shell is 2 pi times the radius times the height times the thickness. We want the radius and the height as functions of V sub k in this case. So that's what our typical sum is going to look like in the Riemann sum. The radius in this case is going to be Vk minus C. The thickness is just going to be delta V. And the height, well, height is an interesting description. You really have to turn your head to see it as a height. But the height is going to be the top minus the bottom. And you're going to have to get that information from the problem as it's given to you. But once you find all this, then you're able to put that back in. So here's how your shells fit together. And now look, this interval right here accounts for all the shells. So our integration is going to take place from V inner to V outer. You go inside to outside in this case. Let's look at a particular example. 3 minus 2x squared and square root of x. We're going to take this region and we're going to spin it around the y-axis. So we're going to get a shape that looks like a top, and we want to find the volume of this thing. We could use washers that could stack along the y-axis. You'd have to break it into two integrals, but we're going to use shells. So we're going to imagine how the shells fit together. We're going to notice that the skewering axis then is the x-axis. This integral is going to be with respect to x. We have to find all the relevant quantities with respect to x. So here's a prototypical x and a shell that goes with it, and we got to find everything in terms of x. Our radius, pretty simple in this case, it's just going to be x. Our thickness, delta x. And our height is going to be the top minus the bottom, and that means our height is going to be 3 minus 2x squared minus root x. Now notice that in this case, if you go from 0 to 1, you will take into account all the shells. So this time the integration runs from inside to outside, i.e. from 0 to 1. Putting it all together, there's our volume integral. But let's double check. Here's our radius, our height, and our thickness. And then we can multiply this out and apply the usual tricks, and actually this integral is pretty easy. So let's summarize. Using the method of shells to calculate volume. So you have a region that you're going to spin around an axis, and you have to visualize how the shells fit and then concentrate on a typical shell. You have to identify the skewing axis. So in this diagram, that would be the u-axis. You have to calculate the radius and the height as a function of that skewing variable u. You have to identify the innermost and outermost values of u for your integration. And then you put it all together and integrate with respect to u to find the volume. Now in this case, we're going from the innermost value of u to the outermost value of u, but it could be that a shape is given in such a way that you're concentrating on the piece where you have to integrate from inner to outer. So it's ambiguous. It depends on the kind of shape you have. You might be integrating from inner to outer or outer to inner, but either way, the form of the integral looks the same.